In this video, we're going to talk about the concept of proportional. So when you say that two quantities have a constant rate or ratio comparison, we could call that proportional. So an example would be there are 7 days in a week, always. Every week, there's 7 days. So the number of days is proportional to the number of weeks. So they ask the question, is the rate 14 days over 2 weeks equal to 7 days over 1 week? And the answer is yes, they're equivalent. And the reason they are equivalent is because um, 14 days is double of the 7 days and 2 weeks is double of the 1 week. So in other words, we can reduce 14 days over 2 weeks to be 7 days over 1 week by dividing top and bottom by 2. So yes, they're equal. If we double the number of weeks, the number of days will also double. And that double is happening because these two things are proportional to each other. Distance in feet is proportional to distance in yards. So write the constant rate as a fact and as a fraction. So we have a way of comparing feet and yards. So if you didn't know, and you could Google this if you like, there are 3 feet to every yard. So I could say that 3 feet equals 1 yard. That would be how I'd write that as a constant. As a fraction, you could write 3 feet over 1 yard. Or you could even switch it if you wanted, if that makes sense. Oops, 1 yard over 3 feet. So when quantities are proportional, we have this idea of scaling, which we've talked about previously, to convert. So let's look at an example of what that means. A homeowner is updating their electrical wiring to accommodate the power needs of a new appliance. The distance from their circuit breaker to the desired location of the outlet is 28 feet. The wiring is sold in yards. How many yards should the homeowner buy? So using the idea that we know that there is 3 feet for every yard, we could think of this as taking 28 and dividing it by 3. That's one way to do this. But if I wanted to try to use the scaling idea here that they refer to, scaling to convert, that means I'm going to actually use one of these fractions to write my conversion. So instead of just dividing 28 by 3, what I would do is multiply it by 1 yard over 3 feet. Now, technically, I said they both work, right? But the reason I like the 1 yard over 3 feet is with fractions, we can reduce what's in the denominator with what's in the numerator. But what that does is that allows us to cancel, quote unquote, feet. We want feet to be the thing that cancels in the numerator and the denominator. And what I'm left with is yards, how many yards this is. So using fraction multiplication, I'm going to multiply straight across, numerator times numerator. So 28 times 1 is 28 yards. And then in the denominator, I would have just a 3. No measurement, because the idea was feet canceled out. And what I can do is grab my calculator, take 28, divide that by 3. And I think you should do your calculator too. If you don't have it, go grab it. And I'm getting 9.3 repeating, which I'll just round to 9.3 yards. So that means in order to have enough wiring, I'm going to need to round up and buy 10 yards. I suppose I could do 9.5. That would be relatively safe. But always better to have a little extra in case there's some sort of issue, right? So 10 yards would be safe. So this idea of multiplying like I did here with these two fractions, that's a common technique for proportions. Okay, so let's kind of see if we get a chance to look at that again. If the distance to the outlet was 30 feet, how many yards is that? Okay, so now we're working with 30 feet. And I'm going to still multiply by 1 yard over 3 feet because I want the feet to be on top in the numerator and in the denominator, because then they cancel out and I'm just left with yards. Again, multiplying straight across, 30 times 1 is just 30 yards. 1 times 3 is just 3, no measurement. And 30 divided by 3 is 10. All right. So a distance of 0 feet is how many yards? Well, it seems like a silly question, but the answer is 0. It isn't a silly question. We'll talk more about that when we are looking at proportions and determining whether things are in fact proportional. Okay, let's look at another example. A barista earns a minimum wage of $10.25 per hour. The pay is proportional to the hours worked. And for right now, we'll disregard taxes and tips just to make it really easy. Okay, so let's write the pay rate as a fraction. So as a fraction, they get $10.25 for 1 hour. Or we could write it as 1 hour is $25. So we can write it either way, and we'll pick which way we want to use based on what unit we'd like to cancel. So in these particular problems, numbers 4 and 5, our answer, we were asking how many yards we have. Oops, I'm sorry. How many yards we have. That's why we wanted yards in our answer. So we intentionally chose to get rid of feet so that we would have yards in our as the unit of our answer. Okay, so if a barista earned $181.94 last week, how many hours did he work? Write and solve a proportion. Okay, so that means that we're starting with his amount of money. So if I want to pick which fraction from number 7 would be nicest to multiply by, I'm going to want to pick the second one. The reason is it's got the dollars in the denominator. Oops, I switched it to red, but the computer was not ready. Dollars in the denominator. And that means that the dollars will cancel with the dollars in the other fraction. Now, notice I didn't write the unit dollars. I could have literally wrote out, and here, I'll just do that really quick. You don't have to write this, but I literally could have wrote out 1 hour. For some reason, I didn't write out the word hour either. And $10.25. I could have wrote it like that so that I'm canceling the word dollars. I got a little bit lazy. I used the abbreviation HR and then the literal dollar sign, but it's going to work the exact same way as it did in the last problem because the dollars are going to cancel. And what I'm left with is 181.94 times 1 is just 181.94 hours. So hours are staying. And 1 times 10.25 is just 10.25. No units in the denominator. So I'm going to be left with hours, which is what I wanted. So I'm going to grab my calculator, do 181.94 divided by 10.25 and get 17.75 hours. So I'm rounding, excuse me, I'm about to cough there, to the hundredths place. Because 0.75 makes sense when we're talking about 3/4 of an hour. All right. If he doubles his hours, what happens to his pay? His pay will double. And they're asking these questions because we're about to see some examples where it's not proportional and we need a way of knowing that. So this is an example where something is proportional, just like the last one. It's an example of something that was proportional. So we're trying to keep these ideas in our head about how we measure that. So one is, if you double one, does it double the other? That's a very basic question to ask if you are wondering whether two things are proportional. The next basic question to ask is right here, number 10. If he works 0 hours, how much does he get paid? $0. And that was the same thing for the 0 yards and 0 feet. Okay, that matters. Those are two questions we want to ask ourselves when we're looking at whether or not things are proportional. Okay, so now it is possible to have two units of measurement that are not proportional. This means that if you double one, the other isn't necessarily doubled. It also means that if one measurement is 0, the other might not be. The example we're going to look at is temperature. So we're going to look at the difference between Celsius and Fahrenheit. And as you see, they've labeled the boiling points. For Celsius, it's 100 degrees. For Fahrenheit, it's 212, and that's for water. And then they labeled the freezing points. 0 degrees for Celsius, negative 32 degrees for, no, I'm sorry, just 32 degrees for water. That is not a negative symbol. And you can see that when you're looking at the measurement on the right for Fahrenheit, which is about 75 degrees right there, that ends up being 25 degrees or so Celsius. Okay, so they tell us there's actually a formula to convert between the temperatures. All right, let's use the formula, fill in the table with the correct temperatures, and the first one is done for us. So they've given us a bunch of Celsius measurements, and we're going to fill in the Fahrenheit using the formula. So here, let me scroll down a smidge so I can see the formula. So for Fahrenheit, I'm going to take the Celsius temperature, which in this particular one is 0. I tried to give myself enough space here, and you're going to want to get your calculator. So 0 times 1.8, that's what that little symbol is time symbol. So times 1.8 plus 32, which is just going to be 32, which actually they labeled that in the picture for us, right? 0 degrees Celsius is 32 Fahrenheit. Cool. All right. All right, 10 degrees. Let's do 10 degrees. So 10 times 1.8 plus 32. So that's going to be, plugging that into my calculator, 50. Then they did the next one for us. And let's do the next one, 30. So 30 times 1.8 plus 32. So putting that into my calculator, I am getting 86. The last one, 212, is the Fahrenheit, and they want us to figure out the Celsius. Well, we could probably guess based on the pattern, right? Based on the pattern, we could probably say it looks like it's, you know, there's an increase of 10 each time for Celsius. Is there an increase for Fahrenheit? And the answer is actually there is. It's increasing by 18. If I add 18, that gets me to 50. And if I add 18 here, that gives me to 68. Oops, that's supposed to be an 18. And if I add 18 here, that gives me to 86. So how many times did they add 18 to get to 212? That's kind of the question. We could go ahead and subtract 212 and 86. Which gives you 126, and then divide by 18, which gives you 7. So they had to add 18 7 times. Which means they'd have to add 10 7 times. So adding 10 7 times means we get to 100. But again, really quick, we actually know that information. They gave that to us on the picture. 212 is 100 degrees Celsius. So they actually gave us that information. There is another way of finding out the temperature. If what I did makes sense to you, and what I'm about to show you doesn't make as much sense, that's fine. You can, you know, what I've done here, you can stick with it. But the other way is to basically use the methods we just did above in reverse. So for the formula says take the Celsius temperature, times it by 1.8 and add 32. So for Fahrenheit, we would do the exact opposite. Sorry, I didn't mean to erase that. For Fahrenheit, you do the exact opposite. You would take 212 minus 32. So instead of adding 32, I'd subtract 32. That gives me 180. And then instead of multiplying by 1.8, I would divide by 1.8. Here, let me write it as a division symbol. And when you divide that by 1.8, it gives you 100. So you would do the other way of doing this is do the opposite of the formula. So the opposite is subtracting 32 and dividing by 1.8. That's the exact opposite of what the formula says to do. Sorry, that 1.8 is kind of sad looking. 1.8. Okay, either way, we get 100, either method you feel comfortable with. And of course, like I said, it's actually on the picture, so we really didn't need to do that work. Okay, when Celsius temperature doubles from 10 degrees to 20 degrees, does the corresponding Fahrenheit temperature double? And the answer is no, it didn't double. It increased by 18, but when it went from 50 to 68, right? That's what we're referring to here, 50 to 68. Let me select the blue pen. This is not double, even though this doubled. So that is indicator number one, that it's not proportional. So no, it didn't. Does 0 degrees Celsius correspond to 0 degrees Fahrenheit? Nope. No, it doesn't. They talked about that in the picture. 0 degrees Celsius corresponds with 32 degrees Fahrenheit. All right. So are they proportional? The answer is no. Not based on what we talked about previously. So an increase of 2 degrees Celsius is the same as an increase of 3.6 degrees Fahrenheit. So is the above statement saying temperature 2 degrees Celsius is the same as temperature 3.6 degrees Fahrenheit? And the answer is no, no, because it's using the word increase. An increase implies an addition. All right, so they're not telling us the comparison between Celsius and Fahrenheit. They're telling us when you're talking about an increase of Celsius, it ends up equating to this increase in Fahrenheit. So let's look at the thermometers. The freezing point of water is indicated as 0 degrees Celsius, same as 32 degrees Fahrenheit. That's the thermometer picture above. Use the formula to find the Fahrenheit equivalent for 2 degrees Celsius. All right. So using the formula, I'm going to plug in 2 degrees Celsius, times it by 1.8 and add 32. So 2 times 1.8 comes out to 3.6 plus 32. I'm getting 35.6, which I will squeeze in there. So clearly the above statement is not saying that 2 degrees Celsius is 3.6 degrees Fahrenheit. What it is indicating, though, is that an increase of 2 degrees Celsius, here they're adding 2, ends up being an increase of 3. So is the same as 3.6 degrees Fahrenheit to go from 32 degrees Fahrenheit to 35.6 degrees Fahrenheit. Awesome. So let's take a look at the temperature for 4 degrees Celsius. Okay, so according to the previous page, 10 degrees Celsius is the same thing as 50 degrees Fahrenheit. Oh, 50, not 15, 50. 14 degrees Celsius is the same as, okay, let's figure that out. So using the formula, I'm going to take the Celsius times it by 1.8 and add 32. So 14 times 1.8 is 25.2 plus 32. I'm getting 57.2. So this is 57.2 degrees Fahrenheit. And I'll fill that in all the blanks they have on this paper. So there we go. I don't know why I did this in green. It's bothering me. And even though it's slightly anal retentive of me, oh, well, I'm going to fix it. 35.6. Okay. Thus, a 4-degree temperature increase. So this side increased by 4 degrees. Made this side increase by 7.2 degrees. I see that because it's a 50 and then it increased to 57.2, right? Kind of easy to see that it's 7.2. All right. So 7.2. But since it's double, 4% is double of 2%. I'm sorry, 2 degrees. I said percent and I meant degrees. 4 degrees is double 2 degrees. 7.2 happens to be double 3.6, by the way, which is what we saw in number 7 and what they told us in that statement in the box. All right. Temperature increases in Fahrenheit are proportional to temperature increases in Celsius. So that's different statement. Temperature increases are proportional to temperature increases. So the size of a Fahrenheit degree is always 1.8 times the size of a Celsius degree. However, temperatures in Fahrenheit are not proportional to temperatures in Celsius. We cannot use proportions or scaling to convert between Fahrenheit and Celsius temperatures. All right, so let's create a graph by plotting the ordered pairs we had on the previous page and then connect the dots. Now, they were really nice to label this graph where the left side, the left axis, that vertical line, we call that axis, is the Celsius temperature. And down below is the Fahrenheit temperature, the horizontal line or the horizontal axis is the Fahrenheit temperature. So they very clearly labeled that for us. Let's go ahead and use the ordered pairs they gave us. So the first ordered pair was when Celsius is 0 degrees, right? Fahrenheit is 32 degrees. So 32 degrees Fahrenheit is right about here, right? Wouldn't you say? Somewhere right there. But since it's 0 degrees Celsius, I'm going to actually put the line or the dot right on the line. That's going to indicate 0 degrees Celsius, but 32 degrees Fahrenheit. Okay, then when they went to 10 degrees Celsius, sorry, I'm going to scroll back up. 10 degrees Celsius was 50 degrees Fahrenheit. 10 degrees Celsius, 50 degrees Fahrenheit. So 50 degrees Fahrenheit, that's right here. 10 degrees Celsius would be right here. So there would be my next dot. Then it was 20 degrees Celsius was 68 degrees Fahrenheit. So 68 degrees Fahrenheit, that's right about there, close to the 70. 20 degrees Celsius is right here. So I'll put my dot right there. So I'm like intersecting the two values, 20 degrees Celsius with the 68 degrees. This one's the 10 degrees Celsius with the 50 degrees. And this one happened to stay on the line because staying on that line means 0 for Celsius. Okay. I'm going to erase my little dots. That's just for you to kind of see where these points are coming from, especially if it's been a long time since you've graphed. That's where they're coming from. I'm just lining them up on the Celsius line and the Fahrenheit line. Okay, so then it was, I think they did 30 degrees. I'm almost positive, and then they skipped, right? Yes, 30 degrees Celsius is 86 degrees Fahrenheit. Sorry, my computer just lagging out there for a second. Oops. It's very upset at me for touching the screen. Get over it. There we go. Stop it. Okay. 30 degrees Celsius. It's 86 degrees Fahrenheit. It's so mad at me. All right. Get over it, computer. Okay. 68 plus 86. Okay, so 86 degrees. Let's see, the halfway mark would be 85. So just next to that halfway mark, right about there. That's about 86 for Fahrenheit. 30 degrees Celsius is right here on the dotted line. So I'll put it just a little to the right of halfway. And then the last one was 212 degrees Fahrenheit matches 100 degrees Celsius. So 212 was like all the way over here. In fact, 212 kind of goes off the page because if that's 200, the next one would be 210 and it's off the page. So I'm not going to bother plotting that one. I'm going to go ahead and connect these dots. And what we notice is they line up very nicely. All right, they line up very nicely. Okay, using this graph that we just did, we're going to talk about other graphs and what that tells us about information. So the graphs represent pay for two different jobs, job number 1 and job number 2. For one of these jobs, pay amount is proportional to hours worked. Okay, so worked, sorry. So let's look at this job here, job number 1, and let's try to figure out the hourly pay for job number 1. So first thing I'm noticing is, even though it's a little bit hidden in the graph, it is a point there at 0, 0. And that bottom axis is hours worked, and the vertical axis is amount of pay. So when they work 0 hours, they get 0 pay. So right there, that's already hinting to me that this thing is probably proportional. That's one indicator for proportional. 0 equals 0. Okay, now let's look at the next piece of information. When we have 10 hours of work, they get paid $200. So if I want to figure out how much they get paid per hour, I'm going to take the $200 and divide it by 10 hours. And 200 divided by 10 comes out to $20 per hour. Now, the next thing I notice is that when it doubled the number of hours, when they worked 20 hours, they got paid $400. So when they worked double the hours, they ended up getting double the pay. So again, that says to me, this is probably the job that is proportional, that the pay is proportional to the amount of hours worked. So the answer will be yes. We figured out the doubling and the 0 equaling 0. All right, so let's look at job number 2. Let's find the hourly pay rate for this job. So for this job, when they work 0 hours, they're getting paid $200. All right. When they work 10 hours, they're getting paid $400. Interesting. So first thing I'm noticing is that they had an increase of $200 per hour because they worked 10 hours, right? So there is an increase of $200 in the amount they get paid for working 10 hours. So again, like the last problem, $200 for 10 hours of pay equates to $20 per hour. So they are also getting paid $20 per hour. The difference is they have like a base pay that they're guaranteed to get every time. And that's $200, even if they don't work. So maybe their salary, right? Maybe their salary, and then they get a certain amount of overtime, or maybe it's just the way the job is written. They get that pay because of the hazard that they deal with or something like that. I noticed that when we double the hours, 20 hours, it goes up to 400. Oh, I just realized, oh, goodness me. Look, 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 I just made a mistake. I just realized it, 10 hours of pay, that's actually $300. Uh-oh, sorry, let's fix it, which means it's an increase of not $200, but $100, which means this is $100 over 10 hours, which is $10 per hour. Aha, okay, difference. So their hourly rate of work is less, all right, than the other job, but they're getting a like guaranteed pay amount of $200 even if they don't work. Let's verify that that's in fact the case. So when I look at 20 hours of work, they're getting paid $400. So when they increased the pay from 300 to 400, they worked another 10 hours. So yes, $10 an hour does in fact make sense for this. Okay, so now they say, is it proportional? And the answer is no. It doesn't have doubling, right? When you double the number of hours worked, it didn't double the pay, right? It didn't go to $600, it went to $400, so it didn't double the pay. Then they said, okay, so which job would you rather have? And explain. Okay, now this is a little subjective. For instance, if you don't want to work a lot of hours per week, I would say the second job works very well. So if you don't work a lot of hours or can't work a lot of hours, the second job is better. So if you're doing like a side hustle, the second job would work out great. But for most people, the truth is the first job is better, because at 40 hours a week, they get $600, but here 40 hours a week, they get $800. So in the end, when they work a full work week, which is typically 40 hours a week, they're getting paid more. So it does make sense. The first job is better overall if you work full time. The first job is going to pay better. So if you're okay with a small amount and small amount of hours, great. But otherwise, you're going to want the other job, the one that pays more per hour. Because even though they give you this nice little bonus of you don't work, you still get paid $200, you still are going to end up making more in the end in the first job versus the second job.